Dear friends, welcome. My name is Johannes. Today we will have a precise lecture on open channel flow. So in this topic, we will have different types of flow in open channel, and also we have classifications of this open channel, and also different characteristics, and also velocity and pressure distribution in open channel flow. So let's see the detail now. So we have open channel, which is a very important topic in hydraulics. So under this topic outline, we will have types of flow in open channel and the properties of open channel, velocity distribution, pressure distributions, and also geometric elements of open channel section, and computations of uniform flow, compound channels, and equivalent roughness, and the design of most economic cross-sections of this open channel. So I hope in the previous course we were dealing with closed conduit flow, and in which the water surface is not exposed to the atmosphere and it may not be subject to atmospheric pressure. But in open channel hydraulics, since it is open to the atmosphere, so it will be subject to atmospheric pressure. But in closed conduit flow, only hydraulic pressure exists. So I think let's see the detail now. So we have open channel. It may be defined as a passage in which liquid flows with upper surface exposed to the atmosphere. So it will be exposed to the atmosphere. So we will have open to the atmosphere. So upper surface or water surface is open to the atmosphere. So we have examples like culverts, spillway, and also similar human-made structures like secondary canal, main canal, and also other drainage structures. But closed conduit, we may have water supply distribution systems and also irrigation pipe networks, etc. But here it will be open to the atmosphere. So types of flow in open channel, we can just classify into the different types of open channels depending upon the change in the depths of flow with respect to space and time. So with respect to space and time, we will classify such as steady flow, unsteady flow, uniform flow, non-uniform flow, steady non-uniform flow, or steady uniform flow, etc. So I hope it will be just dy by dt, or the change in depths with respect to t, which is time, and also with respect to space or x distance, dy by dx. So let us see the detailed definition. So we have flow. First we have flow. So this flow may be steady flow or unsteady flow. So this steady flow, which is just, it may vary with respect to time. So you may have uniform flow and varied flow or non-uniform flow. And unsteady flow, same, you have unsteady uniform flow or quasi-uniform flow, and also unsteady flow, which is unsteady varied flow or non-uniform flow. So we have just varied flow or non-uniform flow. It could be gradually varied flow or non-uniform flow, and also rapidly varied flow. So we will see these topics in detail in the next chapters. And also you may have unsteady flow. It could be gradually varied unsteady flow and also rapidly varied unsteady flow. So let's see the definitions of each types. So in open channel flow, the flow in liquid has a free surface to the atmosphere, and the liquid is not under pressure other than that caused by its own weight and by atmospheric pressure only. So it has its own weight, which is just exerting to the bottom of the channel, and also you have atmospheric pressure on the top surface. So what do we mean by steady flow? So steady flow, if the depth of the flow velocity, and flow rate at any cross-section of the channel do not change with respect to time. So it will be constant. So there is no any change with respect to time. So you have steady flow. Unsteady flow, which is if the depth of flow and also flow velocity and the flow rate or discharge at any cross section of the channel vary with respect to time. So you have time criterion. So steady and unsteady flow, you have time criterion. So you will just compare with time. So but uniform flow, if the depth, slope, cross section of the channel, velocity remains constant over a given length of the channel. So there is no any change in these parameters with respect to distance x. And non-uniform flow in a channel is said to be non-uniform or varied when the channel depth varies continuously from one section to another section. So if you have, for example, this is a channel going like this, so at a distance x, what will be? So non-uniform channel. So it will vary, which means the depth. For example, if this is y1, then at this point it will vary. So y2 will vary. But if it is uniform flow, there is no any variation with respect to this x distance. This is x distance. And the steady uniform flow, the depth of flow does not change during time interval and space under consideration. So steady time criterion you have and space criterion. So both just there is no any change or does not change during time interval and also space under consideration, which is distance x. And unsteady uniform flow, this is uniform flow, but you have unsteady. So this is a flow in which the depth is varying with time. It may vary because of unsteady, but not with space. Not with space. It will be constant. And unsteady non-uniform flow is the flow in which the depth is varying both space and time. So if it varies, unsteady non-uniform flow. So these are velocity and pressure distributions in open channel. So if you have triangular channel, you may just see this type of distribution. And in trapezoidal channel, you can have like this. At the top, you may have some space between these streamlines or these points due to just the cross section of the channel. And if you have narrow rectangular channel, at the bottom you have a space, but here congested. So this is congested at the top due to just circulation, but at the bottom you have some space. And shallow ditch you can see, and pipe, if it is partially full, you have like this. Just through the periphery of circular channel, you can just see like this. But if you have natural irregular channel like river or any other natural channel, you have like this. So this is open channel, free to the atmosphere. So pressure is exerting on this water surface. Pressure variation in horizontal channel, you can see this just distribution in the channel. For example, you have this horizontal bed of the channel. If datum is taking under this, then you can have some just Z elevation to this point A. Then you have such types of hydrostatic pressure distribution on this one. It is triangular. At the bottom you have gamma H at this point, since you have H height. And you have at the point 1 and at point A, so you can calculate the pressure at any point below the water surface. So you have Y depth at this point and H depth at the bottom. So from this data, you can just calculate PA over gamma, which is pressure head, which is PA over gamma, is equal to Z1, which is this one above the datum, minus ZA. Z1 minus ZA will give you this depth, so that it will be Y depth. So pressure at A is gamma times Y. So you can have gamma times Y. So this is just how you calculate the pressure at any depth. But if you have some inclination with this theta, with this measurement, it will be changed. So at this point, you can calculate the pressure at O. Since you have some inclination, so you have to compute gamma y times cos theta. Gamma y times cos theta is this one. So you can just calculate at this point gamma y times cos theta. So the equation will be pressure at A times change in L distance for this distance L. For this distance L, you will calculate gamma times y change in L cos theta. Since it is inclination, so you have to multiply by cos theta. And pressure at A will be gamma y cos theta. Since it is inclination, you have to consider this one. Then finally, you can compute using this equation. Pressure at O, which is at this point, the bed, you have gamma times h. Since you have h height from this up to this point, and h cos theta. Since you have inclination, so you have to consider this inclination angle. Then finally, P naught over gamma will be h cos theta, which is d cos square theta. So d is just the distance from this point up to this point. If you take vertical, but this is inclined, you have theta here, so you have to compute this dimension, then d cos square theta. Okay, so pressure distribution in curvilinear flow for convex and concave channel, we will see this one. So this is, for example, convex channel. So you have this point, so you have R up to this point, up to the center, up to this point, R distance. Then you may have again up to 2 points, you have R2, then you have R1. Then you will just calculate normal acceleration, which is normal centripetal acceleration or normal acceleration will be v square over r. So I think let us see. So you have such types of distribution. So you have y depths below this water surface since it is curved. So flow is coming to this direction. Then finally it will go like this. Then the distribution will be like this. So since you have just hydrostatic, then R2 minus R1 will be H. So you have R2 from here up to here. And R1 is from here up to here. So if you subtract, then you will find H distance. Then you can have such types of hydrostatic distribution. So since you have hydrostatic distribution, since from the top up to the bed of the channel, so this is the bed of the channel, which is curved, then you can just calculate gamma y minus n normal acceleration y times over g. So you can take out y, then it will be gamma y, then you can have 1 minus n over g. So this is just the distribution from here up to here, from here up to here. Then this will be just the change, which is gamma n y over g. And this is also again at the bottom you will have such magnitude. This is the magnitude at the bottom of the channel, and then total you have gamma h. But we need this calculation, which is gamma 1 minus n over g times h from here up to here. So total h you have. Then finally we can have p over gamma plus z. Z is, you can take datum here, then pressure head, potential head equal to normal acceleration over g times r plus c according to Euler's formula. Then finally you have z1 minus z minus n over g. Then you can calculate this value. So once you have this, then you can just calculate these results. So this is p over gamma times you at a. At this point you have 1 minus an over g. So we can take gamma here to this one, then gamma times y, which is the pressure at this point for convex curvilinear channel. But for concave curvilinear flow, which is flow is coming through this direction, then it will go like this. It will go out here. So if you have datum here, which is z is going, then at this point you have bed of the channel, and here water surface at 1, then you have H depths and Y depths at point A, then you can calculate the pressure at A. Similar approach, you have to draw the hydrostatic pressure distribution for this curved channel, which is concave. So you have Y depths. So at Y depths, you have gamma times Y here. But due to this curve, you have this additional pressure, which is gamma An Y over G. So An is normal acceleration, which is V square over R. Then you have at the bottom, and also from here up to here again, you have this one. Then finally, you can compute the pressure at A. The pressure at A, according to Euler's formula, you can just P over gamma plus Z equal to integration of V square over GR dr plus C, which is constant. Then you can just compare again. If V is constant, which is mean velocity of flow, you can have sometimes if V is C over R, then you have free vortex model, and if V is C times R, forced vortex model. Otherwise, N is equal to constant, which is V square over R, normal acceleration, radius of curvature at midpoint. At this midpoint, you have R. So you will just calculate using this equation. Then finally, at any point A, at radial distance R from O, you have this equation. This equation, Z1 minus Z, V square over G, ln of R over R minus H. So R is up to the bottom of the channel, and R is at any distance. At any distance from the center of the curve, then you can compute P over gamma. And then you can consider again this theta angle. You have R minus R, capital R plus H, cos theta plus V square over G, ln of R over R minus H. Then finally, you can just consider this one as final pressure at any point A, Y times 1 plus An over G. Okay, so the next topic is geometric elements of open channel section. So open channel, you have different cross sections according to the shape. It could be a rectangular channel, trapezoidal channel, or sometimes triangular, or sometimes circular channel. So I think it can be defined entirely by geometry of the section and the depth of the flow. The depth of the flow. So depth of the flow is Y, we can say. Top dimension T, stage height H, any H height, weighted perimeter P, which is water is touching the boundary of the channel, and also weighted area. You will just calculate hydraulic radius or hydraulic mean depths R. Hydraulic depths, again, you have D, conveyance of the channel, and the section factor or ZC of at critical or normal. Just section factor for critical condition, critical flow, or normal flow condition we will have. So I hope, let me just, okay, I think you have rectangular channel. So in rectangular channel, what is the area? B times Y. And weighted perimeter, B plus 2Y. B plus 2Y. So you have B, then you multiply by this one, 2Y. Again, hydraulic radius, area over weighted perimeter. So this is hydraulic radius, which is area over weighted perimeter. Weighted perimeter is just this one. Y you have here, Y here, then B plus 2Y. Top width is equal to the bottom dimension, which is B, etc. So you have this one. We will see for each channel. I hope if this is not clear, I think I have other format, or I think this is more clear. So you can see for rectangular channel, you have such type. Area is B times Y, B times Y. This is just B times Y. You will have for different channel geometry. So we have such formulas for computation. So let's go to uniform flow in open channel. So what is uniform flow? Uniform flow will be developed if the resistance is balanced by the gravity forces. So if the resistance of the channel, which is just due to the property of the channel bed, it is balanced by gravity force, it will attain uniform flow. So uniform flow in open channel has the following main characteristics. Uniform flow. So from the very beginning, just we see uniform flow, steady flow, and also unsteady flow, non-uniform flow, etc. So as the name implies, uniform means just there is no any change with respect to x. So the depth, water area, velocity, and flow rate or discharge at every section of the channel are constant. So there is no any change. And the energy line, water surface, and channel bottom again are all parallel, and their slopes are all equal, which is slope of energy line and also slope of water surface and bed slope equal. So they are parallel and equal. There is no any shifting. So you can see this is just slope, bed slope. Why not you have? So these energy lines are parallel to each other. Okay, so flow computation formulas. We will see section factor for critical flow and also normal flow condition and uniform flow computations again. We have conveyance of the channel, hydraulic exponents, and flow in compound and composite channels. So section factor for uniform flow, it is just nothing, the product of water area and 2/3 of the hydraulic radius. So the product of water area, which is this one, then 2/3 of hydraulic radius. So this is section factor. So this is section factor. So this section factor you can substitute in AR 2/3. Then finally you can see Qn over radical S0. So section factor will be either Qn over radical S0 or AR 2/3. And conveyance of the channel is nothing, just the discharge capacity of the channel per unit longitudinal slope. So discharge capacity of the channel per unit longitudinal slope, longitudinal slope will be conveyance of the channel. So conveyance of the channel is nothing, you will just have N, here N. So you have this formula again for conveyance of the channel. So A over N R 2/3 equal to Q over radical S0. Q over radical S0. So this is the general equation for conveyance of the channel, and for section factor is this one. So we will come to this one after a minute. And calculation of normal depth and velocity, you have here, you can just bring this Manning equation. Q is equal to A over N R 2/3 plus times S0 to the power of half, or sometimes velocity is 1 over N. 1 over N R 2/3 times S to the power of half, or radical S0, or sometimes you may use Chase equation if you have resistance coefficient C, then you can use this Chase coefficient C square root of R times S0. S0 is the bed slope and R is the hydraulic radius of the channel. So if you rearrange from Manning, for example, if you take this one, Qn over radical S0, then substitute in place of area, R, etc. R is area over weighted perimeter. Then if you substitute all the geometric elements as the previous table, then you can have N0, say N0 equal to Y0 over B. Take out Y0 over B from the equation. Once you substitute, for example, for rectangular channel, if you substitute the equation, area is By, then R, which is hydraulic radius, is area over weighted perimeter, which is area is B times Y over B plus 2Y. Then take out B from all. Then finally, if you take b to the power of 8 over 3 to this side, then you will find this equation. So this equation is for rectangular channel having n naught is equal to y naught over b. So once you calculate n naught by iteration, you can find normal depths, this one, for rectangular channel. For trapezoidal channel, again the same. You just substitute in place of area, which is b times b plus my times y. So I think I can bring the previous format. This is just for triangular channel. Again, for trapezoidal channel, you can have area is b plus my times y. This is area of the channel, and weighted perimeter again b plus 2y square root of 1 plus m square. So since you can calculate this side slope length, you can calculate. So since you have 1 to m, then you have here m times y, here again m times y, then you can calculate my. Since this is perpendicular, then you can calculate my y square, my the whole square equal to this slide. Then you can have this one 2 times both sides, b plus 2y square root of 1 plus m square. Then after rearrangement, you can see this formula for computation of this discharge or normal depths. You can have normal depths, just crisscross for trapezoidal channel. And for triangular channel, you can have this formula. You can use this equation. We will see examples. And for circular channel, again, Qn over radical S naught d to the power of 8 over 3 equal to 2 theta minus sine 2 theta the whole 5 over 3 over 32 theta 2 over 3 ar 2 third over d to the power of 8 over 3. So from table we can read out. Then finally you can arrive at the solution, which is normal depths. So here you must be careful. So this is just in radian measure. So any theta which is circular channel which is subtended, you can have theta. So this theta should be converted into radian measure. Here again you can convert into radian, then substitute here. Then finally you can arrive at the solution. So area of the channel is this one, d square over 8. 2 theta, again this is in radian measure, but here you can substitute, since you have trig, sine, cos. If you have, you will substitute in degree measure here, but here in radian measure. And 2 theta is 2 cos inverse of 1 minus 2y over d equal to f of y over d. And the top dimension of the circular channel is d sine theta and t d theta. So let me again go back to the screen, which is this format for circular channel. For circular channel, you have this is subtended angle by the chord of water surface. Then you have area, perimeter. You can have r hydraulic radius, top dimension, and diameter. Then finally, after rearranging, you can find. So we will just read out this calculation. Then finally, you go from table, just this one as a function of y over d. You can read out. Then finally, just crisscross by this one. You can find diameter may be given. Then finally, you can calculate normal depths, critical depths, etc. I will come back to this one after some minutes when we do examples. So I hope we have some sample problems. We will solve these problems using iteration or using table, etc. So if you have any question, you are welcome. Otherwise, we end up chapter 1 with. And thanks for watching this video. So this is all about today's lecture. Hopefully you liked the video. If you have any comment or question regarding this topic, please write down in the comment section below. I will reply on it. Please like, share, and subscribe this video to get more precise lectures. Thanks.